Hi, everybody. My name is Puyan Jamshidi. I'm assistant professor at the University of South Carolina, and I'm the PI of this NASA project. It's called Raspberry Pi. In this project, we plan to enable autonomy with AI and machine learning. And I'm delighted to be here with my colleagues for this project. This project is a collaboration between University of South Carolina, Carnegie Mellon University, University of York, and University of Arkansas, and we closely collaborate with several researchers at NASA JPL and NASA Ames. We are all part of the program. It's called ARROW for Autonomous Robotics Research for Ocean Worlds, which is managed by Caroline Mercer. So science discovery and quest for finding another form of life in other planets are one of the most important missions that as humans we explore. The current practice of science discovery on remote planets are heavily influenced by scientists and human in the loop. So we send space landers, rovers, helicopters in other planets, but due to delays, there are several issues that may arise. For example, obviously, the communication delay, several hours between Earth and a planet such as Europa moon, which takes several hours, would result in high delay in science discovery, high mission cost, high risk, and this obviously doesn't scale if you want to increase the number of space rovers on another planets. And obviously, the most fundamental or challenging aspect is dealing with unknowns. So in this project, we plan and we are developing technology, mainly AI and machine learning technology, to replace some of these tasks with automated procedures. For example, for perception, for synthesizing new plan to deal with unknowns, we are doing it with the AI and ML technology that we are developing in this project in order to address these challenges. In particular, in this project, we focus on missions related to Europa lander. And next, my colleagues, Ellen and Catherine, are going to talk more in details about these scientific aspects of the project.
Hi, everyone. My name is Ellen Zaplinski, and I'm one of the science consultants on this project. I recently obtained my PhD in Space and Planetary Sciences at the University of Arkansas, where I experimentally study organic processes on Titan.
Hi, my name is Catherine Cirilla, and I am a fourth-year PhD candidate at the University of Arkansas. I'm also working as a science consultant, and I am working on my dissertation observing Titan organics. The search for life in our solar system has led scientists to focus on ocean worlds. Prime examples of these ocean worlds include Europa, Enceladus, and Titan. Although we are designing our project to be applied to a variety of ocean worlds, we are choosing to focus on Europa as a test case.
What characteristics of Europa are scientifically interesting?
Well, there are several important characteristics that make Europa a great candidate for possibly finding traces of life. First, a subsurface liquid water ocean interacts with the surface and may create plumes, allowing a lander to sample this material. Second, interesting features like lineae and cracks point to a geologically young surface. Lastly, possible chemical reactions on the surface have the potential to form the building blocks of life.
When thinking about sending a mission to the outer solar system, what are some of the biggest obstacles?
To date, no lander operated on the surface of Europa. This will pose new and exciting challenges for mission design. High radiation, low gravity, and low surface pressure on Europa are all variables that will be encountered during a mission. Furthermore, the location of icy bodies in the outer solar system will present the need for new technologies required for mission success. The distance from Earth to these ocean worlds causes a communication delay over an hour because they are so far out in our solar system. Therefore, visiting their surfaces with spacecraft will require autonomous software due to the limited communication with Earth. Now, Bradley and Javier will discuss the techniques of the autonomy module.
Hi, I'm Bradley Schmerl. I'm a principal systems scientist at Carnegie Mellon, and I work on engineering autonomous systems. At Carnegie Mellon, we've been researching self-adaptive systems for a couple of decades. And out of this research and research of our peers, there's emerged a common way to engineer self-adaptive and autonomous systems called the Make-K loop, which specifies the components that are often needed to achieve autonomy, centered around a knowledge base that is continuously updated. For this project, we focus on adding autonomy to mission execution, particularly in managing excavations. We don't interfere with any existing low-level autonomy that may be on the lander already, for example, for managing arm movement. And so in this scenario, the lander is tasked with identifying and excavating terrain around the lander, giving priority to digging locations that have potential to uncover evidence of organics. So the way we put this together for this project is by having monitors that monitor the state of the environment, the terrain around the lander, the status of the robot itself, for example, its battery level, and the status of the plan that's currently being executed. We then use this knowledge to analyze the execution of the lander to determine whether the plan has failed or is performing suboptimally. If this is the case, we then synthesize a new plan on the fly, taking into consideration this new and updated knowledge. And this plan is then given to the lander to execute, hopefully reacting to any problems or failures that might have occurred earlier. One of the novel aspects of this research is that the knowledge part is augmented by machine learning models. For example, we may use machine learning to identify a list of candidate excavation locations that we would use. For this project, we will use a framework called Rainbow, which we developed at Carnegie Mellon, and we've used this in a variety of autonomous contexts in the past. And now Javier will talk in more detail about how we achieve the planning.
Hi, I'm Javier Cámara. I work as a lecturer and researcher at the University of York in the UK, and I'm a collaborator in this project working on the automated planner of Raspberry Pi. The planning process receives as input information that is monitored, updated in the knowledge base, and analyzed at runtime. This information is about the state of the system and the environment in which it is operating and includes alternative candidate locations for excavation and dumping materials, including attributes that include the predicted science value of the various locations, as well as their excavatability, which is encoded as a probability of successful excavation. In the planner, the information obtained from monitoring and analysis is incorporated into a formal specification, which is synthesized by a model generator component. The specification is analyzable by the Prism probabilistic model checker and encodes a Markov decision process that encodes non-deterministic choices among alternative actions that can be performed by the robot. These choices in the Prism model are left underspecified so that they can be resolved by the probabilistic model checker in the next step of policy synthesis. A policy is a specification about which actions have to be selected in each of the available choices, in such a way that some quantitative objective can be optimized. Such objectives include the maximization of the probability of successful excavation and science value, as well as the satisfaction of time and energy constraints. In the next stage, a high-level plan specification that includes the choice of excavation and dump locations is extracted from the policy that was generated by Prism. In the last stage of planning, this high-level plan specification is translated into a fully fledged Plexil plan that can be executed by the robot. Producing this Plexil plan specification entails incorporating low-level details that are transparent to the planner but are required to produce working Plexil code. Now, Jianhai is going to talk about evaluation.
Hello, my name is Jianhai. I'm a third-year PhD student in University of South Carolina. In this project, I'm working as a research assistant. My research is focused on the reinforcement learning, transform, and autonomous computing. So in this project, we plan to use 2 testbeds to evaluate our autonomy module. One is virtual testbed developed by the NASA Ames Research Center, which we call the Ocean Waters. The other one is a physical testbed called the OWLED, developed by the NASA JPL. The reason we want to have 2 testbeds for evaluation is that for the virtual testbed, it can provide more flexibility in simulating instruments and the environment. For example, the light condition caused by the position of Europa, Jupiter, and the Sun. And for physical testbed, it is more closer to the lander, therefore it has like a higher fidelity. For example, during a digging operation, the actual force and torque can be measured in the OWLED, while in the virtual testbed, it only can be simulated. So the physical testbed, short namely for OWLED, its setup has like 4 main components: the platform, the manipulation arm, the surface material simulants, and the perception tool. Right now they use a camera. For the arm, they actually implement like 7 degrees of freedom arm, which mounted to the lander platform with one raised force and torque sensor, also 2 changers. For the platform, it's actually installed 3 force and torque sensors. This is used to try to capture any movement caused by loading different amount of material in the scoop. And they also have modular instruments which could be mounted to the robot arm to conduct different operations. On the left 3 column actually representing the interrogation instruments, which try to figure out the geotechnical property of the surface. On the right 2 columns, they actually a scoop and drill. Scoop is for collecting loose granular materials. The drill is to handle harder materials. Also, they implement hardware in the loop simulator for the lander and the manipulator. The reason for this one is they want to make sure any autonomy which will be tested against the hardware testbed will actually be will not violate any security boundaries. So they will actually test in their software simulator first. The way they make it happen, they provide a same collection loss action for both the software simulator and the real hardware testbed. The virtual testbed Ocean Water, developed by the NASA Ames, they simulate different type of surface. For example, the salt, the regolith, and the rock appearance. Also, they implement a lighting model to enhance the visual appearance. In their lander model, they have simulated the actuated arms, also implemented the kinetic models to avoid the collisions. Besides that, they also have other tools like antenna, camera, scoop and drills. One more interesting thing is they also implement the power and battery modeling, and also they are actually implementing the fault injection. For the surface arm interactions, they actually use analytical scoop model, which will be real-time approximation, which will be really useful when we do the simulation. You will see, okay, the scoop has actual effect on the appearance. Now, Abir and I are going to use the virtual testbed to show the self-adaptation of the lander when encountering a fault in an excavation scenario. The reason for choosing excavation in the demo is that it is the first important task in the Europa lander mission. Hi, Abir, could you introduce yourself?
Hi, my name is Abir Hussain. I'm a PhD student in the Computer Science and Engineering Department at University of South Carolina. For this project, I'm working on developing the machine learning models. So, Jianhai, could you please explain what is the excavation scenario?
Sure. In the excavation scenario, the lander will need to identify the optimal excavation dump location given a list of locations. Just as highlighted in the screen, we have 8 excavation locations and 6 dump locations. After that, the lander will dig the trench and remove debris. The optimality here refers to the maximization of digging success and the expected science value of collected samples on the limited budget of energy consumption and time cost. The approach we used here utilized Prisma probabilistic model tracker to first build a model using the given list of excavation dump locations, then export a polyspec query it against a given property, which encodes a multi-object optimization problem, and then extract a high-level plan from the policy, finally translate it into a Plexo plan.
Is there any uncertainty considered in this scenario which will cause a system fault and therefore probably fail the plan?
Yes. So simulated fault has been introduced to the model that estimates the accessibility of a location. The fault actually could be caused by multiple uncertainties. For example, the level of noise on the sensors of surface interrogation instruments could rise drastically for a short period, resulting into inaccurate sensor readings. The introduced fault here makes the model incorrectly predict the accessibility of the selected location, xlog1. Its actual value is 0.0, while the model's estimation is 0.8822. This partially contributes to its winning selection during planning, but leaves a high risk of digging failure.
How will the autonomy module or the lander react to this failure of the excavation plan?
To adapt to the excavation failure, the lander will have to do a replanning, but the replanning will take consideration of the updated runtime information. That is, the location xlog1 will not be considered anymore. As seen, the newly selected location for excavation is the location xlog3, whose accessibility is 8836. In this time, the model prediction is not affected by any fault. Therefore, it is expected to see a digging success with a very high chance.
Why the self-adaptation is important for the lander operating on ocean wall, for example, like Europa?
The self-adaptation enables the lander to counter against the internal and external uncertainties automatically, which are quite common in space missions, and could cause faults and lead to potential failure of land operations. The capability of self-adaptation becomes more important for space missions like the Europa lander mission, where the involvement of experts on the Earth need to be minimized because the mission period is limited, which is about 20 days, while the round-trip communication between Europe and the Earth is relatively quite high, which is up to 1.5 hours. Thank you for watching the demo.
Thank you all. So I would like to summarize this project. As I mentioned, and it is one of the most important aspects of this project is the collaborative aspect of it. We heavily collaborate with several scientists and researchers at JPL and AIMS. As you know, our team is also diverse from multiple universities, from multiple different backgrounds. So we are all excited to be involved in this project. We discussed about the ideal vision for science discovery using AI and machine learning in remote planets. Hopefully there are chances of discovering interesting scientific aspects through these innovative technologies. And also we discussed about the science part of this project. And at the end, we discussed about the technical aspect, how we develop, and what is the position of autonomy in the whole vision for science discovery. Thank you all. And please, if you have any feedback, questions, and if you want to contact any of us, all of this information can be found on the project website at NASA, Raspberry Pi, github.io, Raspberry Pi. Thanks.